Yes, sir.
Okay, so let us get started. Is the presentation visible?
Yeah, yes, sir.
Okay. Good morning, friends. We have been discussing the UML diagrams for modeling systems. And just to again remind you of the context, we have discussed about a variety of behavioral diagrams besides the detailed structural diagram of classes, where in terms of the behavioral diagram, we have the most abstract level of use case diagram. And then we have discussed about sequence diagram, talking about the sequencing, temporal sequencing of messages, the communication diagram, which is about spatial distribution of messages. How does different objects collaborate by passing messages? We have talked about the activity diagram, which is primarily in terms of expressing the procedures that are involved. So it's as you have seen, is it's a significantly enriched form of flowchart with very detailed specification of algorithmic steps, including those of expressing concurrency in terms of fork and join kind of operations. The concurrency, or it could be parallel also. So it could be parallel processes or concurrent processes, whatever. And finally, we are talking about state machine diagrams, which in a way define the behavior in terms of certain states and the transitions that happen between these states. And we looked at a basic example here in terms of ATM, where we conceptualize the different states of the ATM as we operate. Now, at this point, you'll have to start putting in your mind that at what level of abstraction we conceive this behavior is a choice of the design. It may be at a very high level, like as you see here, the machine is could be in idle state, wherein it means that it is not being used, not in being used, but ready for use. It could be in active state, which means that a customer is doing some operations on the machine, trying to withdraw cash or check balance or something of that sort, or obviously he or she is using the credit or debit card and so on. And it could be a state where the machine is not usable, out of service. Now, obviously, if you think about, say, at least primarily the active state, you will be able to reason that the active state could have a number of states that it will go through. Like being active is, say, if I say is tapping on the screen, then there is a state where the card is put in or not put in. If the card has been put in, whether the pin has been given or not been given. So you can think about a lot of subsequent states that actually are involved in the machine remaining active. So there is no absolute definition for, there cannot be an absolute definition for what is a state. It depends on the level of abstraction that you want to look at, right? And we'll see how this kind of a hierarchical specification of the system being in multiple granularity of states can be modeled through the same behavioral state machine diagram. This was another example of a temperature controller that we looked at. Again, that same thing applies, that the machine could be idle and could be in a cooling state or heating state, or could be in an error service state and so on. And each one of them may actually have a number of substates, sub-substates, and so on. So we check that this is naturally the state machine being that it will have vertices, and it will have behavioral transition, because every state is kind of describing a behavior, a situation in the system. So one state to the other will happen through a certain behavior change. So to put in kind of a somewhat of a little formal definition, though it is not formal in the mathematical sense, but in the conceptual sense, the a state models a certain situation. Often it is implicit, where an invariance hold, like in the ATM. Being in idle state means nothing is happening in the machine. Being in active state means there is a customer and the customer is interacting with the machine. Being in out of service state means that it cannot be used, and so on. So it may represent a static situation such that, for example, an object is waiting for an external event. For example, in idle state, it is a static situation, because the machine is expecting an external event like tapping on the screen or insertion of the card to happen to make transition to some other state. Or a state could model a dynamic condition, like such as the process of performing some behavior. Like active is more a dynamic condition, where a process for doing some transaction, whether credit, debit, or just check balance kind of thing are being done. So it is in the process of doing that. So it is kind of working or things like that. And to represent this, we can have a number of kinds of states. Like what we saw so far are just simple state. There could be composite states. There could be sub-machine states. So it's basically, I mean, I was mentioning about the hierarchy. So you are trying to basically do the breakdown and create that hierarchy using different kinds of states. So to present a simple state is one which does not have substate. So just the state itself will tell you what it is. So it has a name which may be optional. And for example, here you have one simple state which has the name but nothing else. Then there could be internal activities, that is what you do, the behavior, while you are in the state. And additionally, there could be an entry activity as to on what you entered that state, or an exit activity as to on achieving what you get out of that state. So waiting for user input, the what you are waiting for is an entry, and what you exit is kind of a thanks, and so on. What you actually do is not shown here. And there could be internal transitions, a list of internal transitions where each item has the form of what we call a trigger. I mean, trigger is basically a transition, but it's a more detailed description of the transition, as we'll see. So this is a simple state. Like this is described in terms of simple states and simple triggers. Like this is a state of describing the phases of water. We know water can be in multiple phases, typically 4 phases. So liquid, solid, gaseous, or plasma. So here, if we have water vapor, which is we can say is a gaseous state, it can go to plasma by ionization and come back by deionization, and it can get into ice directly or go into liquid, and so on. So these are the simple state descriptions. Here is another example where we use simple states, but specify in a little bit more detailed manner. You can see that every state has a name, right? Some states have only name. Say like this is where you start. So there's a dial tone. So there is a do shown in many of these. Do is what is the activity that you do, right? So specifically entry and exit are not being shown. It is implied that the transition or the trigger will tell you what is the entry and what is the exit. So you have a dial tone. That is what when we when we start trying to call up someone. So in that state, the action is play dial tone. Right? And then we keep on pressing the digits, which is this trigger where it is you dial a some digit. So once you do that, you get into a dialing and kind of continue to be there. You are dialing digits, and you see what is shown typically. We have seen this notation earlier also. This is kind of a guard condition that you continue in this till you are incomplete, that you have not finished. So what there are the three possible exits that you can see here. I dial something which is invalid, say not a number or not what is expected. So you get into the invalid state, and the action that you do is play a message that you have dialed something which is not correct. Or you could have given a significant amount of pause between dialing two digits. So here, just arbitrarily set it as 15 seconds. So you get into a timeout state. Say, okay, you have taken too much time. So yeah, I cannot proceed any further, timeout. Or you have completed the dialing. And if you have completed the dialing, then it gets into, so you can see a more detailed description of a trigger where the action is on this transition, the action is dialing digit N, which is the last digit. The guard condition is that it has to be valid. And then what you do on this is do to connect, right? So you make a transition to connecting. And then in connecting, you can have a busy where it does play a busy tone, which is the activity, and or it can get connected, so where it gets into a ringing state and do play ringing tone. Then the callee answers, so enable the speech, so you get into the talking state, and the callee hangs up, so you get to the pin state. The callee answers, you are in talking state, and so on. Right? So these are, you can get to timeout by just pressing and not dialing anything, kind of similar to what you have here. Then the caller hangs up, you disconnect, get back to the idle state. You lift the receiver, you start in here again, and so on. And you'll see that many of the states finally do not show a transition. For example, busy state or transition out of that state, say like the timeout or invalid or busy. So those are all shown together here, that these are all. So it is not shown, that means it is it's kind of is aborted, right? You aborted, terminated, right? So this is kind of how you typically depict a behavioral state machine in terms of simple states, right? So now you can have a composite state. A composite state comes with the concept of level of abstraction, as I was talking of, that I am in a state, and while I remain in that state, I could be doing a series of things, a sequence of things, or periodically I could do certain things. So those can again be described in terms of behavioral states and transition. So you can first look at this diagram, that the state is serving customer. And this is what is the simple composite state, which has what is called one region. These are called regions. So you're saying the state serving customer, where I start, and I have two sub-states here, which are nested. One is I get into and first do an authentication for the customer. To service, you will say, okay, hello, who are you? Give your this, give your that. I'll ask you your date of birth, confirm the date of birth, and so on. So there's a customer authentication. And once that is done, then you get into the transaction. Right? Here, several other details like what happens if authentication fails and so on are not shown. So supposing that authentication always succeeds. and that gets you to a final state. So this is a substate. This is a kind of transitions in terms of substates which are shown. And the substates could be sequential, that is disjoint, or they could be concurrent, that is orthogonal in that way. And they could be shown in terms of regions. So simple composite state has just one region, as you see here. In terms of orthogonal composite state, may have more than one region. That is, to describe this high-level state, I may have two or more different kind of state behavior that is possible. So it is like a decomposition compartments show all of that. I can show it, show this composite state also in terms of a abstraction. So what you are saying is serving customer is a composite state. I mean, if you do not draw this kind of, which is looking like a dumbbell, actually it is saying that I have a substate and another substate and there is a transition. Just symbolically, it is trying to say that. The decompositions actually, I mean, how many substates you have, what are the transition, what are the substate names and so on are hidden. But all that it is telling in terms of the diagrammatic depiction is that this is a composite state, right? So this is, you could also may not expand and just say that this is a composite state and expand it somewhere else. So you can see that there is always a multiple level of abstractions that is allowed in terms of the diagram. So this is on left is one example of a non-orthogonal composite state, because it has only one that you can have. So I mean, abstract example. So you have two substates and there are events which make the transitions between these substates and a final event which takes you to the final state. And this is where you have two orthogonal composite, two orthogonal regions, where being in composite state, you could either be here or you could be here, right? So it could be between substate 1 and 2, or you could be between substate 3 and 4, right? So all these possibilities. Let's look at a more realistic example. So I mean, realistic, but very high level. So this is the behavioral diagram of how we live. So you are born, and so the state is human life. You are alive, and finally, we all end up with the end of life in death. And there are two regions describing. One region is talking about your marital status. So you are single, then you may get married, so you get into the married state. Unfortunately, some of us go through divorce or separation, so you get into this state. You can remarry and so on. So this is one kind of set of substates and transitions that you can be in. At the same time, you could be in that is the reason it is orthogonal. So this is talking about one aspect of being in the human life. The other aspect of being in the human life is someone could be unemployed, or could take up a job and be employed, and unfortunately might lose the job and become unemployed again. So these two do not interact between them, but these are two different aspects of what keeps on happening in detail while you are in this behavioral state of human life, right? So this could be disjoint, that either this happens or this happens, or it could be like in the situation here where it is concurrent. I mean, you have a marital status as well as an employment status at the same time, right? So that is the basic idea of composite states. You could depict that very explicitly by doing a notation of disjointed substates or parallel substates. You could say that these regions, so these are like ABR regions, like you see here. So if you draw them like this, then it is called parallel. So it's a AND refinement. All substates are active when the superstate is active. So when I'm alive, both my marital status as well as my employment status are active. So they're in parallel, they're AND. Or I could depict them in this way. So this is actually not a state, this is a region now. So I could be in this region or I could be in this region, right? So You could have disjointed subsets or refinement in that way. So these are the composite states, or I can actually take this notion even further to have orthogonal submachine states. That is, I could have a complete decomposition into submachines altogether. That I could have another FSM which describes a certain state. So let's look at this. So what I mean, when you do composite state showing substates, or when you do submachine, again is a matter of judgment. When it is kind of somewhat simple to describe in terms of substates, you will possibly do a composite state. When that itself gets quite complex, then you will possibly do a submachine. So in terms of submachine, what you do, you draw it separately. So here, let's look at that FSM in little bit, FSM activities in little bit more details, particularly when it is inactive. So you come in, you verify the card. If the card is accepted, that's a trigger. Then you get into this read amount, right? So you need to know what is the amount that. So we are kind of assuming that it is inactive, and the activity that we are looking at is kind of withdrawing money. That's it in the ATM. That is the most common thing that we do in ATM. So this is a submachine. Read amount SM is a submachine. Read amount submachine, and if this machine succeeds, then what you get is a read amount, and you can proceed further, like verify transition. Or this could lead to out of service, or this could be aborted, like the transaction. I mean, reading that amount did not happen. So if you verify the transaction, then again, the rest of it is not shown. Actually, dispensing the cash, giving you the receipt, and all that are not shown. But you release the card. Similarly, when on abort also, you release the card. Now this submachine, read about submachine has this. So you start doing that. So if you have used ATM, you'll see that often ATMs have certain amounts which are given. Say how much you would withdraw, 500, 1000, 2000, like that. There are a few common common amounts that are given. So you could select from that. If you select, then you have already got a read amount. You come back here. Otherwise, you say, no, these are not. I want to enter. I want to, withdraw 1200 rupees, which is not there in the selection. So I choose the other amount. I enter that amount. If I successfully enter that, then I come to this. Okay, I've got the read amount. Otherwise, from both of these, there is a possibility of I said, no, this is not what I want. You abort. And so if you get the read amount, you have got the read amount to proceed to verify transaction. If you have done an abort, you are here and you directly release the card. So you can see that here, behaviorally, you are into a state where Y, which we'll describe as this is the state in which I read the amount. But that process itself has a lot more of detailing in terms of what is the reading amount. So that is what we show as a submachine. Now you could say that, couldn't I have drawn this as a composite state? Yes, I could have. I could have put this in the compartment in a region within this, but I'm choosing to do it differently because it is turning out to be complex. In reality, submachines. So the choice between a submachine and a composite state is, as I say, subjective. Simple 2-3 states, few transitions, you'll do a composite state. If it is more complex, you do a submachine, and very often you do submachine. For example, here, for example, the select amount itself could be a composite state by itself, because you choose as to, which the first one, the second one, the third one. So you could go in terms of that and then select, or the other one do a select. So like that. So this is kind of a little bit blown up example of the ATM. So you come in, it is kind of off. So you turn it on. So these are different triggers that are happening. So the trigger is turn on, and the action that happens is the machine, starts up, gets into a self test. I'm sorry, If that fails, it gets into out of service. Otherwise, it gets into idle. Right? In idle also, it could have issues, so it get into the maintenance state, out of service, and maintenance could handshake between them. And if it is out of service, typically the machine, if not serviced, could go back to the off state. Now, if the self state succeeds, then I get into an idle state where I insert the card. As I insert the card, I get into a servicing customer state, which is a composite state, as we have seen. So that has an entry condition of reading the card and the exit condition of ejecting the card. So this is what you do at the entry and exit of the state. And then you have different substates: customer authentication, selecting transaction, and the transaction itself. And as you can see by this notation, that we are not blowing up and showing it here, but it indicates that somewhere I will talk about this customer authentication substate, which in turn is a composite state, that it has further substates. Transaction has further substates and so on. So it goes on like that. Overall, when the servicing customer is done, either by cancellation or by successful completion, you get back to idle and remain in idle till you turn it off, which is shuts down the machine and puts it back to off. So different examples just to realize the level of abstraction that you do in here. Right? So that was about the basic behavioral state machine. I will just go on and talk a little bit in terms of pseudo states. Pseudo states are kind of they are states, but they are kind of may not always be corresponding to a physical situation. You could decide to have something as a pseudo state because that is how you prefer to do the modeling. This is a repetition of that. So a pseudo state may have may include the initial pseudo state, terminal, entry point, exit point, choice, fork, join, and so on and so forth. So this is the initial pseudo state. You have already seen terminal pseudo state. So this one is a pseudo state, right? This is not something which is this solid circle is not a reality. It's kind of your depiction that this is where you start. This is a depiction that this is where you end. So these are kind of our pseudo states. You can have a pseudo state which is an entry point. You say, okay, this is a state and have a substate, and this is the entry point of that. This is the exit point of the state. So these are all pseudo states. These are kind of depicted as states, but they do not have that, and they have a predefined behavioral interpretation of you are starting up, you are ending, you are entering, you are exiting, this kind of. And extending this, it also allows kind of things that we did in activity, that you could have a choice pseudo state. That this is a little bit higher than what your normal FSMs will do. So you could have a choice pseudo state where you have a decision being made based on the guard conditions, a binary decisions or a ternary decisions on an n-ary decision. Similarly, you could have pseudo states like fork and join. So these are states, but this is a pseudo state, the fork state, where you say the transition comes, the control comes in here in my AND, then both of these trigger simultaneously. So we saw these concepts in terms of in terms of the activity transitions between those activities. Here, the units are states where there could be further details. You remain there till certain things happen and so on. But these are the additional kind of enhancement to the normal, usual transition where you say we are in a state, get an input, go to the next state. We are enhancing those by using this kind of pseudo states. So this allows you to specify state machines which have their own kind of concurrent behavior. So these are major additions to the traditional FSM that you see in terms of the state machine model in UML. So you can fork here, you can join here, and Then there are some states which could be junction. We say the junction state. Like this is you could depict it in several other ways also. But what we are just a easy way of depicting is, for example, we are receiving messages from multiple different ways, right? This one is voice, SMS, and fax. So possibly the time when this diagram was done, fax was very relevant and others were not. You could think about a voice message, you can think about SMS, you can think about WhatsApp, you can think about email. So there are different ways we receive messages. And after receiving that, we could respond through any one of these, right? So it's not, I could have got an SMS and I responded in WhatsApp. I could have got a WhatsApp, I responded in mail, and so on. So I can reply based on, whatever I choose to be the reply channel. So this node, this state here depicts that it is a junction. It is a decision-taking junction, and it is just depicting that I can come here from any one of these and go from here through any one of these. So it's a bifurcation in that way, right? So there is no condition check or anything. So because of that, it's not kind of a choice pseudostate. You saw choice pseudostate. It might look like a choice pseudostate, but choice pseudostate is where we have the guard conditions, and here it is just showing in terms of the guard conditions as to what choice are you making. That's it. So it's a simpler depiction. You can choose between the two depending on what depth you want. This is another that's an enrollment process. So enroll, term started, the student is being taught, and when the classes end, the final examinations happen, things get closed, and you come to the final state, another pseudo state. Now during this, a student drops out of enrollment. When a student drops out of enrollment, then you check whether there is any student left. I mean, is sum inner size greater than 0? Then, I mean, if a class does not have a student, or it may not be 0, you could have a minimum number also. If it is, if does not have that number, or if that does not have a student, then you cannot continue teaching. So naturally, the sum inner size is 0, means you terminate. Otherwise, you go back and taught. So this node is a junction state where you are taking this. So you can see that this is something which is very similar to a choice pseudo state, but it's a more compact representation. Whenever that can suffice your purpose, then you could, because it here you are not basically may not be saying what your choice condition, but you are just saying it in terms of the guards that you put. Then you have history states. There are two kinds of history states: shallow history state and deep history state. They're basically the same. So history state is something that well, while we are doing an operation, and maybe there is an interruption on that operation, right? So I'm on the state machine. There's an interruption, and when I start up after the interruption, do I start from the beginning, or I start up somewhere near where I had actually ended? So history is about remembering where I had been interrupted, right? So you're saying that you have a washing machine which does washing. When it runs, it does washing, it does rinsing and spinning. I don't know if you have operated a washing machine, you'll know it then. Then there could be dryers and all that. But if there's a power cut, which is an interruption, then the power is off, so it's nothing is happening. When the power restores, it does not, I mean, should not. I cannot say does not, depends on the machine, but it should not get back to the beginning of washing. It should restart from where it had got interrupted. So that's a basic concept of. So you're saying that when you get back here, you don't, when the power restores, you don't go back to this initial state, initial pseudo state, but you come to a history state, right? Which is a little bit more difficult to maybe maybe detail out slowly. You will have to detail this out, but you say that you are getting back to a history state, which means that if you have been rinsing, you should get back to that. If you had been spinning, you should get back to that, right? So that's the kind of behavior you say in terms of the history pseudo state. So H is a pseudo state here. There are some more examples you can read through. I will not go through those. These are self-explanatory. And obviously you have a final pseudo state, which is always there. So these are the examples that we saw through. Toaster oven is another example you can go through. There's a more detailed example. I suggest that you take a little bit of time and try to go through this. I collected it from somewhere, I forgot. This is a state machine of a simple calculator, which does different operations. So you can see a calculator can be viewed obviously as a state machine, and that's what is being described here. Now, before I close, a little bit of word about the behavioral transition. So we have looked at the transition as going from one state to the other. A transition is actually between a source vertex and a target vertex, obviously. But it could be detailed in terms of a trigger, a guard, and a behavior expression. A trigger is kind of what causes it to happen. Guard is the condition that must get satisfied for this to happen. And behavior expression is what you do on that transition, right? So, and you can see each one of them is within a square bracket, which means that they are optional. So I said that traditional FSM can be modeled in terms of this state machine. So in a traditional FSM, often we will not have any one of these. I'd say A to B. A trigger on count, on I have a guard on count, and so on. Right? I have a behavior expression in terms of saying that if I make transition from this to this, then this is the output that I make. Right? So you can see that this behavioral transition description of state machine model in UML is powerful enough to represent whatever you have already known. And then a trigger could be any collection of triggers. Guards are obviously constraints. Behavioral state machine that we saw already. So this is what I just I have it here because just in case you have not done operating system, but when you do, you will live with this diagram for weeks. So this says that what happens to a process in the operating system typically. So you create a process which has a state which is new. So a new process gets admitted into what is called a ready queue, because there may be multiple processes running, but you have only one processor. So at a time, you can only run one of them. So processes that are ready to be run is in the ready state. And then they go into the running state. There is a scheduler which decides as to which of these processes must run. So that goes into the running state. Only one process can be in the running state, of course, because you have one processor. So it is in the running state, and obviously it cannot continue running forever, because then other processes will not get service. So what you do, you have some kind of a timer or something which interrupts that process, interrupts this running of the current process. So on that interrupt, that process comes back to the ready queue, and scheduler probably will schedule some other process. So it depends on strategies and all that, but at a very high level behavior, that's what is happening. Now, while running, the process might need some input or output, might need to read a data, or might need to write something, and so on. And typically, as you know, that input output is a much slower process, slower activity compared to the execution. So when I need to read something from the input, or I want to write something, then I will give it to the device driver of the corresponding device, input device or the output device. So when I do that, that process at that point is not ready to continue, right? Because it is not ready to continue because it cannot, if it is expecting an input, it cannot continue without getting that input. If it is expecting to output something, it has to complete that output process. So In that case, from running, it cannot go back to ready because it cannot be scheduled immediately now till this IO operation is done. So it puts onto a different state, different behavior state, which is waiting. Right? And the scheduler knows that the executing process has gone out of the running state, will put some other process from the ready back to the running. Now, at some point of time, the input or output that was expected to happen gets over. Some other interrupt happen, the completion of event, and then this process is brought back from waiting to ready. It cannot go back to running because something else is running now. So it will go back to ready because it's now ready to execute again. Right? And finally, when a process completes while running, it goes to the terminated state because it's done. It does not need to run any further, so it cannot go back to ready. So this is a very high level and diagram of what happens to this is called process state transition diagram, which is what I'm placing in the context of a behavioral state machine model. You will live with this diagram through your OS course and subsequently your comprehensive Viva and all. This is a very pet question of the examiners that describe me the process state diagram. Just an example of a behavioral state machine here. Right, so that's that I think is brings us to the end of the behavioral part. Now there is another part of the behavioral state machine which are called protocol state machines, which are just refinements of the behavior state machine. I will not go through the slides. I would rather just describe it at a top level, that a protocol state machine is a specialization where the way you say that is a protocol state machine is you write protocol here. And in a behavioral state machine, your primary focus is on the states. States have to be very, very well defined. And then transitions are defined at multiple granularity. As you saw, that triggers could be at multiple granularity. In a protocol state machine, it primarily talks about the protocol state transition. Right. The more emphasis is on how does the transition happen. Right. So you are specifically trying to say how is the transition happening. So like in here, the part of the processed state. So it's ready to running. You are not describing much in terms of what this ready means, what this running means, what is inside, but what you want to focus on is what is this transition. That protocol is thread selected by scheduler to run. Then it goes here. The process running has its timeout, so it yields to other process back to ready, or for some reason the scheduler has suspended it backs to ready, and so on. So this is protocol state machine is where your primary focus is in terms of the protocol state transitions here. So when you want to detail, so you can have a behavioral state machine and then kind of refine it to a protocol state machine as well, or you can directly do a protocol state machine if that's the main emphasis. For example, here you can see for the keyboard operation we are showing a protocol state machine more because the states you can see are blank, just the names are given, default caps lock. But here the transitions say everything very explicitly, that how you kind of make the transition on caps lock, on toggling that caps lock. What happens when you press any key? Any key is the trigger, and the behavioral action is sent lowercase scan code. Here also the same thing. So these are the triggers, these are the actions, initial transition, and so on. So it's basically not a significant difference, but it is just that you have more of the dynamic behavior. I said that state is either the static behavior or the dynamic behavior. So it's more of the dynamic behavior that you are trying to capture. Just I mean, you will find this example in detail in module 11, but just to put you in context that this is trying to model an static properties. So which just describes the make, the model, which does not change. But the red ones are the dynamic values. That is, as the elevator moves through the shaft going up or down, Then it has the dynamic behavior of which floor it is in, if it is moving or standing still, if it is moving up, moving down, whether the door is open or not. And based on that, you have a more detailed protocol state machine for that. Here, I have annotated the states inside just to make things clear, but these are the different protocol actions that you take. So you can see that there's not a very significant difference between behavioral and the protocol transitions, except that in protocol state machine, the transitions have to be very well defined, because that is what you are. So there could be a precondition, the actual trigger action, and the post condition in a transition. Right? So you can go through this. This is another shopping account example. You can see that the states are just names, but we are detailing in depth in terms of what these protocol transitions are. Right? Go through this, take your time, go through this, and you will. This explanation diagram is also given here. Okay? And finally, an example is worked out for the state machine of leave management system that we talked about in slide 18. So this is a state machine which is extracted from that specification. So that's what will might come handy for you, that from the specification this is what you can extract, and this is what can then be modeled in terms of the high level design, and you can code that, because often it might help you to just track in terms of the states than tracking them through the activities and conditions in the activities and so on. Okay, so that this is all about the state machine diagram. There are several others in the UML diagram which we'll skip, as I said. Let me go back to see if there are questions, then I'll take. Otherwise, I have something else to discuss a little bit. Any questions? I think these concepts are simple. All that you need is to just a little bit of practice with examples, and I think the assignments will give you that help pretty much. Okay, so let me just spend a couple of minutes before we close. Let me spend a couple of minutes on the. You may have received the mail. You may not have got the time to actually go through. I think the mail went pretty late in the night. Is about your next two assignments. They have been released together in the same document. So you have assignment 4 and 5 released together, but obviously you have different submission dates. Now, just wanted to highlight few points about this assignment. So please read this initial note very carefully. This assignment is developing over assignment 3, which is the booking itself. But in assignment 3, the booking was very simplistic. It was just in terms of the booking class. It did not have information on passenger and so on. So what we include now are information of passenger and booking category. Like we know it's not only one kind of booking. I can do a general booking. If I am a senior citizen, then I get certain concessions for booking. If I'm say a differently able person gets different kinds of concessions based on the different ability. There could be booking that I do at a priority. Say we call that Tatkal booking by paying extra money and so on. So there are different booking categories which are brought in, and the passenger information is brought in because certain booking categories are just dependent on the booking class, like you are doing a Tatkal booking. So how much you pay, that does not depend on who is booking. It depends on which class you are booking, what distance you are booking for, and so on, which tells you how much extra you have to pay for this last minute booking. Whereas if you are giving a concession for a senior citizen, then naturally it depends on what is the definition of a senior citizen. Right? It depends on the age of the person. It depends on the gender of the person. It's interesting that in railways, in common, I should say, uh, banks and other agencies, senior citizen is someone who is more than 60 years old. But in railways, the definition is little different. A senior citizen is someone, a male who is 60 years or more, or a female who is 58 years or more. Right? So it depends on, I mean, the whole idea is to say that the passenger significantly impacts the booking, and depending on that, the fare computation logic becomes different. The second that we are emphasizing here is, earlier we assumed that there will be no error. Now we are saying that you have to make the design exception safe. That is, there could be wrong inputs, there could be inconsistency. For example, a passenger has asked for a senior citizen booking concession, but the passenger is not eligible for that. Not say it is the person is 47 years old and asks for a senior citizen. That you cannot do. So you cannot proceed so that never the system gets into an inconsistent state. Then we also discussed that earlier we tried to do some modeling of the booking class in terms of a inheritance polymorphic hierarchy, right? And you must have seen that there is actually not much of hierarchy present there, right? I wanted you to do the exercise to realize that not always there'll be multiple levels. So I mean, some of you have pointed this out. Some of you have done certain intermediate classes because it was asked for, but semantically it is, every booking class has certain characteristics, that's all, right? So it's kind of a single level hierarchy. And here we see that in such cases, and there'll be many such cases where we may not use a polymorphic hierarchy in terms of an inheritance hierarchy, but we could use a static polymorphism. That is, we could use templates and doing a parametric polymorphism. We could do a mix of that. That is, there's a base class, and there are a flat hierarchy of specialized classes, all of which has are different types, different subclasses, but have very similar behavior, at least similar interface, same interface. So in that case, we take recourse to the template based design, because that reduces your code size, that enhances code reuse significantly. So you get to learn more about that and get to use that. Naturally, use of STL has to be extensive. We are also asking for earlier, many of you have done multi file code organization, but the requirement was that it is okay to just do a single file for the entire classes and all that. Here we are asking specifically for a proper file organization with every class and its hierarchy being in separate header file, and their implementation in the source file.cpp and so on. And finally, having done the UML, we want you to follow the formal development process supported by UML, HLD, LLD, test plan, test reports, everything, right? So this is a kind of this note you follow, because you will see that there is a lot of commonality between assignment 3 and 4 and 5. And so what I have done is I have not written it from scratch. Just to help your understanding, I have added or deleted parts. So if you go through the specification, you will see that things have been added new. They are typically marked with a red star or highlighted by yellow. And things that are not relevant or that have changed are basically struck off. So if you see here, for example, we have made changes to the way date has to be represented, so marked here. We have incorporated a booking category, so that is marked here, and so on. Right? So several things are introduced new, and there are items which are not, well, there in assignment 3 are not relevant in assignment 4, those are struck off, so that I mean, you won't get you shouldn't get confused that, well, it was like that, what has happened. So strike off clearly tells you that this is not relevant. So you have a completely new business logic for doing the computation of the fare. Different cases are shown. You have more master data that are provided, and like the previous one, I've given the detailed analysis. For example, for booking class, the analysis has significantly changed. So whatever was there earlier, I've struck off and written the new analysis, because now you need to look at the booking class in a different glasses, through different glasses, given that you have a booking category, right? So it is with you. I just wanted to give these starting words, and the way the assignment 3 and 4 are different is, this is the final task. In assignment 4, you have to primarily do the UML diagrams that we have done, and the design analysis design document. So you do these 6 diagrams for this case, and a detailed analysis and design document, which much of which is actually worked out within this document itself. And in assignment 5, you do the actual implementation, you do the test plan, you do the testing according to the test plan, the test suite, and generate the test report. Right? So this is what the assignment is about. So just wanted you to introduce to that. I'm sure right now you have not been able to see through this assignment, so you may not have. If you have some quick questions, I can try to answer, but you may not have many. As before, send me mails. So I'll try to send clarifications as quickly as I can. Okay, any questions for now? No. Okay, good. So then we will close it here today. So please look at this assignment. It's not difficult, but it needs a good the development of a good understanding of the design process that we have talked of, and particularly the style of handling polymorphism and exception. That I want you to do those very well, and also the test planning and test part. Of course, from the next week, from next Wednesday, I will also do in the theory class also, we will have more discussions on the testing, varied kinds of. Here we are just focusing on the unit testing and the application testing. We'll talk about the testing in general from the next week. Thank you all very much. Have a nice day and a good weekend, and keep sending queries on the assignment if you have, as you have them. Bye.